So, hello everybody and welcome to already the 4th online seminar in our series Science and Society. So, my name is Karen Roelofs and I'm the Vice President of the Association of ERC Grantees. And before we begin, I would like to say a few words about the seminar series and about the format of these events. So the goal of this series is to engage the general public with the fundamental research carried out by ERC grantees, and to highlight the role that bottom-up, investigator-driven scientific research plays in our knowledge-based societies. So over the course of a year, we aim to organize 4 such seminars, one each for the 3 core domains: life sciences, social sciences and humanities, and physical sciences and engineering. And there's always one dedicated more specifically to the links between fundamental research and society at large. So today's seminar is from the physical sciences and engineering domain, synthetic chemistry in particular. And we have the great pleasure of welcoming a very special guest, the ERC grantee and Nobel laureate, Ben Feringa. Ben, you will be properly introduced just in a few minutes by Simon Filetreau, but already a very warm welcome to you, Ben. We also welcome, of course, our 3 outstanding panelists, Professor Stefan Hecht, science journalist Joep Engels, and our very own Silke Bühler-Paschen, who will each be introduced properly after Professor Feringa's presentation. And I already see members of our board on the screen, so welcome everybody. Just a few points before we begin. First, this meeting will be recorded and uploaded to the AERG YouTube channel, where a digest of the event will remain available for later on. And if you want to ask questions in the audience, please use the Q&A function of Zoom rather than a chat. And don't forget to upvote those questions that you find most interesting. And the most upvoted question will, of course, be put to our speaker when the presentation is over and when the panelists have asked their questions. So panel members here, please don't forget to close your microphones. I will now hand over to Axel Kleremans, the president of our Association of ERC Grantees. But before I do that, I would like to express my deepest gratitude to the Necker Institute, who is again hosting us today. So thank you, Simon and Fernanda. With that, I'm done. I see that we have already a nice number of attendees, people connected. So let's going, Axel. Let's get going.
Thank you, Karen. And let me join you in extending my warmest welcome to our speaker. We discussed this in the short meeting we had before we opened the webinar. Professor Feringa played an essential role supporting us early on. He appears in our launch video, for which he shot a small clip expressing a warm endorsement for us on his cell phone. This was all improvised and it was very, very much appreciated. It was amazing for our association to get the support of someone with such prestigious achievements back then. Now, just a couple of words about the association. We're all about defending fundamental research, and this couldn't be more important than it is now, because we're all collectively facing unprecedented challenges, from climate change to pandemics, from the rise of AI to changing demographics. And fundamental research must be funded so that we can be ready for challenges we don't yet know exist. And we think the ERC instantiates exactly the sort of institution we need in order to support scientist-driven, bottom-up blue sky research. And as we build our membership, we will continue to defend this perspective in different ways during the coming year, by organizing our online webinars, by engaging our membership to reflect upon transversal cross-disciplinary challenges, and by making ERC grantees research visible, and also by continuing to dialogue with other stakeholders. So I thank you for your support. If you're an ERC grantee in the audience and you're not yet a member of AERG, please join us. And with this, I will give the floor to Simon, who will introduce our speaker fully. Thank you.
Thank you, Axel. So it is now my great pleasure to formally introduce Ben Feringa, who is currently the Jacobus Van Hoff Distinguished Professor of Molecular Sciences at his alma mater, the University of Groningen. Ben obtained his PhD in 1974 at the University of Groningen in the Netherlands under the guidance of Professor Hans Weinberg. And after working as a research scientist at Shell in the Netherlands and in the UK, he came back, was appointed full professor at the University of Groningen in 1988. He was then named the Jacobus Van Hoff Distinguished Professor of Molecular Sciences in 2004 at the same institution. His research interests include stereochemistry, organic synthesis, asymmetric catalysis, molecular switches on motors, self-assembly, molecular nanosystems, and photopharmacology. In the 1990s, his work led to the construction of the first monodirectional light-driven molecular rotor, and later to the first nanocar, a real, actual four-wheeled molecular device. His seminal contributions to the development of molecular machines were rewarded by numerous awards and grants over the years, including an ERC grant in 2008, and of course, the Nobel Prize in Chemistry, which he was awarded for in 2016, together with Jean-Pierre Sauvage and Sir Stoddart. Ben Feringa holds a remarkable 30 patents, has published over 700 articles. He is a member of the Royal Netherlands Academy of Sciences. He is also an elected foreign honorary member of the American Academy of Arts and Sciences and a foreign member of the Royal Society. In 2008, he was appointed a Knight of the Order of the Netherlands, Lion by Her Majesty the Queen Beatrix. Today, Ben Feringa remains closely associated with the European Research Council, as he was elected a member of the Scientific Council in 2019. In his lecture, titled The Joy of Discovery, Ben will share his experience as a scientist. Dear Ben, it's truly wonderful to have you here today in your multiple roles, as an outstanding scientist, as a Nobel laureate, as an ERC grantee, and as a member of the Scientific Council. Thank you again for being here with us today. Please go ahead.
Thank you very much, Simon. I will start to share my screen. Is that okay? Okay.
Yeah,
I hope you can see it now. Yeah. All right.
Yes.
Okay. Thank you once again, Simon, and also my special thanks to Karin and Axel and all the other people involved. It's great that the Association of ERC Grantees was established, and it's my great pleasure and honor, you know, to talk with you, to share a little bit of my journey through the joy of discovery, my journey, my adventure in the world of science today. So I will talk a little bit about my personal story. I will also give a few experiences, but of course I will also talk about the science and our discoveries and put it a little bit in context. So on the first slide here, you see what we scientists typically do. We go beyond our horizon. That is what science is for, and especially in the context of the European Research Council program, the ERC programs, we want to go far beyond our current horizon to advance knowledge, fundamental knowledge that might change our world in the future. Insights, discoveries, new knowledge in all fields, in the broad context of humanities and science. And of course, sometimes we are looking for the origin of the rainbow, but we will never find it. We know that. This is also science, asking questions and going into unknown territory and being adventurous. And I often get the question, because I work on molecular motors and molecular machines, I often get the question, what is it good for? And this was the same question that the Wright brothers got 100 years ago. By the way, let me check. Can you see the slides? Okay. All right. So the Wright brothers, they were for the first time flying more than 100 years ago. They got the question, why do we need to fly? Of course, we admire the flying bird, but nobody had predicted at that time that we would build in Europe the Airbus that can carry 400 people, 1,000 kilometers an hour, 10,000 kilometers across the ocean. Try to do that with a bird, ladies and gentlemen. The whole construction of an Airbus or a Boeing is completely artificial, 3.5 million parts, but it does its job perfectly. And you cannot carry 400 people, 1,000 kilometers an hour across the ocean with a bird. But we should also be very humble, Because 100 years after the Wright brothers, we still cannot build a bird. We still cannot build a single cell of the bird. We cannot even build one of the machineries of the flying pigeon. So why do we need fundamental science? Why do we need ERC? Why is it so important for Europe, you know, to advance the knowledge? Think about your smartphone. I'm sure everybody has a smartphone. Which were the fundamental scientific questions that were asked? The new insights and discoveries that make that possible. Let me emphasize that it was in the late 40s, early 50s of the past century that the physics and chemistry were developing the first transistors and the liquid crystal materials. Of course, nobody had an idea that we would ever build a smartphone. It were very fundamental discoveries. And in the early 50s, the first computers were built that could do way less than any smartphone that you have today. It took 50 years before we could build that. And when you ask now a student, was there a world before the smartphone? They will say, huh? A world before the smartphone? It has completely changed our world. But it was physics that make the transistors, chemistry that make the liquid crystals and the batteries, engineers, the devices, computer scientists that make the programs, and many more. And don't forget, it was John Goodenow and his colleagues in the 80s that developed the first principle of a lithium-ion battery, that we have the power now to power our smartphones and that we can build electric cars. Very fundamental science, 40 years ago. And again, it changed our world. So when we look to the future, the science, the joy of discovery, we go for challenges, dreams, and opportunities. Challenges for our students, dreams for the people, and opportunities for society and industry. But of course, the most important during this adventure in the unknown is the question mark. And we should not forget that the question mark is not only on this path, because we can have an idea, a plan, but often we deviate and we get completely lost in this beautiful science garden, the paradise of science, and we hit upon questions that we have never thought about. And this is the beauty of science. This might be the most beautiful questions. And of course, serendipity plays an important role when we also address these kind of questions. So this is where my horizon started many years ago in a small village on close to the German border in the northeast part of the Netherlands. And there was a lot of moors. Yeah, and I lived very close to the border. And as a child, we already crossed the German border. This was at that time still illegal. And I think that triggered me crossing borders and moving, you know, the fascination for discovery. And I always felt like this small boy here on this picture, you know. This is this picture, this famous picture of the discovery of phosphorus. And I felt like this small boy. And I always wanted to know. I was reading books about discoverers, about adventurers, etc. And growing up on a farm, this is my parents, by the way, there is a lot to discover. Eh? The cows giving birth to a calf. I asked my father, why is this one flower red and why is the other white? How is that possible? And of course, together with my 9 brothers and sisters, we engaged a lot of adventures on the farm. And this is where it all started, I think, the early part of my career. I, of course, had no idea that I ever would be a scientist. But asking the right questions, being, you know, attracted by phenomena, be curious about Mother Nature, that is where it started. Then, of course, I went to school, to high school. You see here my chemistry teacher, Gerard Op de Weeg. And he said to me lately, when I saw him at a reunion, he said, I wish every child at least one good teacher, because that makes the difference. And I'm sure you all remember one teacher from your high school period that made the difference in your career. Of course, at high school, I became acquainted with chemistry, physics, mathematics, etc. And that set me on the track. I was fascinated by that, by the natural sciences. And that set me on the track to the university. And I had an American professor, Professor Winberg, it was mentioned already. This is, by the way, the main building of the University of Groningen. And he gave me a very tough problem. Yeah, he said, we will make the Americans jealous. Now, this was really what I needed as a kid, you know, very eager, being a student, do research. And this was my first molecule. And when I made my first molecule, I remember I came to his office and he said, Ben, nobody ever made this molecule in the world, not even in America. It was a useless molecule, but I was extremely proud because I did it, I made it. And I was fascinating, you know. And so that set me on the stage. But before I talk about my own research, let me talk a little bit, I'll give credit to our teachers because that is so crucial. They open windows for us to the future, shaping our future with the young talents. And we cannot give them credit enough. And I think many people here in the audience are teachers themselves, but realize you have a very privileged position. So I made a career choice because after my PhD at Groningen University, I went to work first for a national company, Shell, first in the big science research department in Amsterdam, and then for 1.5 years at the Shell Bioscience Center in the UK. And then I decided to go back to Groningen because I wanted to work with students. I wanted to work on very fundamental research and build my own research programs. And I also like teaching. And recently so I want to emphasize when you start your career, and I think many of you experience that, you have to make choices and you ask for advice, because in this adventure, it's very difficult how to make the first steps. And Professor Feringa, who was a very famous professor at Leiden University at that time, he told me, Ben, I can give you only one advice. Choose an important problem. Choose an important problem. Now, I don't know if I choose an important problem, but at least we had a lot of fun and we made some nice discoveries. And then recently on the internet, on Twitter, there was this picture of me, yeah, and it says, we chemists are lucky you choose academia instead of becoming a rock star. I didn't even remember that I looked like this. This was a couple of years ago. This was when I started, you know, fresh in the university, my own group. And I apparently had this quote, the beauty of chemistry is that I can create my own molecular world. And this is what I have done ever since. So creating molecules, that is what we do. Synthetic chemist, I build molecules, being it molecules just because they are beautiful, or molecules because they have a new medicine, or they are a new material, or they will build the sustainable materials for our future. So in the art of building small, I developed a passion for molecules to design my own molecular world together with my students. And so we do chemical synthesis. We build from small molecules, bigger molecules, molecules with specific functions to test theory, build tiny machines, and I will come to that in a moment. So this is what we do in the laboratory. And so we should not forget that in the laboratory, we work together with the young talents, the students, designing all these materials. And we have a universal language, and that is the language of the molecules and the language of the atoms, the periodic table. If I go to China, if I talk in Europe, if I go to South America, wherever I talk and people know anything about chemistry, they know that this is a sugar molecule that I show here. Yeah, and that the periodic table shows the elements that builds up everything, your own body, all the material around you that you see now when you look around you. So we have no borders, we go beyond frontiers. And I think this is also crucial for the European programs, that we go beyond borders, because we have this international cooperation. And our duty is to go beyond frontiers into the future of science and to make the society of the future. So I want to remember to this quote of Louis Pasteur. He mentioned already a long time ago, science knows no country, because knowledge belongs to humanity and is the torch which illuminates the world. And I think more than ever, this is appropriate as we experience that people are fencing themselves in, countries are working on their borders or whatever. I think the science community has a real duty here, discovering our future, but beyond that, also to go beyond borders and build the international communities and strengthen that, the communities, scholars and students. So we know now that this is the molecular formula of the human body. Hydrogen 375 million, oxygen 132 million, carbon 85 million, etc., etc. These are all the elements in the human body, including one lonely cobalt. You might wonder why there are so many hydrogens and oxygens, ladies and gentlemen, but the simple reason is that your body is made 60% out of water, plus a handful of other molecules. So this is rather amazing that your body is 60% water, and then this is the elements that make you all the components in your body that make something complex as a human being. But we also know we can ask the question, are there more elements, distinct elements in your body or in your smartphone? And to accommodate this, I show you this picture, and I can assure you there are more distinct elements in your smartphone than in your own body. And that immediately brings me to one of the pressing issues of our society today, and that is, of course, the scarcity of atoms, molecules, materials, and the recycling, one of the big challenges we are facing in the future. And what you see in red here, yeah, in all this, the green is fine, but in the other colors, you see a lot of materials that are scarce and that we have to take measures to recycle it, to build our sustainable society of the future, because otherwise we have serious problems, including with the lithium for our batteries in our cars in the future. And of course, all these materials that are used to build your smartphone, to build electric cars, to build our windmills, etc., etc. So this is a much better representation than the periodic table that you probably all had in school. Now, as a synthetic chemist, as a chemist in general, we build molecules that can be extremely small, like ethylene, 2 carbons and 4 hydrogens, the basic for plastic, 160 million tons a year for this type of plastic alone. You know, when you have a simple plastic bag, it's made of polyethylene. We can talk a little bit later on the problems of recycling and about the issues of plastic, because that is a major challenge ahead of us. But of course, we can also build very complex molecules like vitamin B12, carbon, hydrogen, nitrogen, oxygen, phosphorus, cobalt, etc. This is essential for your body. Yeah, you need vitamin B12 to stay healthy, but you need only microgram quantities. And the whole world production, as far as I know, is only 35 tons a year. This molecule was built by 2 of the most famous chemists of our era, that were Woodward and Eschenmoser, many years ago, and it was called the Mount Everest of chemistries. So very simple molecules, huge volumes, very complex molecules, very small molecules. That is typically what chemistry does, building molecules. So when you look around you, we make the drugs and the dyes, the cables and the cars, all the components, your clothes of the smartphone, the soaps, yeah, the materials that make I learned that a modern plane is now 50% artificial materials. So this is typically what we do, not in isolation, but of course together with physics, engineering, material science, etc. But that is what builds a modern society, molecules and materials. But what we are not good at is making anything that moves, ladies and gentlemen. So if you think about your body, it is full of tiny machines, the rotary motors, the tiny motors that transport things in your cells, the motors that make the molecules in your body, like the proteins. So the ribosome, for instance, is a fantastic robot that makes most of the proteins in your body. It's an amazing machinery, a very complex machinery. The bacteria flagella motor, you see here in the lower corner. This is a motor that makes the bacteria swim in your guts, making it swimming forward and swimming backward. And then, of course, the optical switching, the process of switching in your eye. And I want to emphasize that there are millions of these tiny switches in your eye, and that make it possible that we can see each other. So the question was, we are so good in making all these molecules and materials that make modern society, but we cannot make anything that makes controlled motion, at least until some decades ago. And this is where we started with this challenge, you know, to introduce dynamic functions. And this all comes down to nanotechnology at the molecular scale. And just to remind you, nanotechnology, the term was introduced, I think, by Richard Feynman in 1959, a famous physics professor in Caltech. And he said, in the event of miniaturization of machinery, there's plenty of room at the bottom. And what he meant, of course, is that you go smaller and smaller and smaller. Yeah, that was you see here the picture of the first computer. As I see, this computer could go way less than your smartphone. And meanwhile, in the past decades, we have gone down and down to the nanometer sizes in our computer devices, the chip technology. But what Feynman said is, look at Mother Nature, look at your own body, look at the green plant. You build a bottom up with small molecules, you build bigger molecules, you make the machineries of life. And this is nanotechnology bottom up. And it took 50 years before Fraser Stoddart, you see his picture here, and Jean-Pierre Sauvage, yeah, we were able to build the first machineries. And together with these two gentlemen, I had the privilege to get the magic call from Stockholm. So, just to bring you all on par, 1 nanometer is 1 billionth of a meter. So it's 1,000 times smaller than a micrometer that you know from a microscope. And the cross-section of a human hair is 80,000 nanometer. So remind you, the cross-section of your human hair on your head is 80,000 nanometers. So it's huge compared to the tiny motors that we make. And you might ask yourself the question, does size matter? Yes, it matters. You all know when you go to a beautiful beach in the south of Europe this summer, and you have this pebble beach, yeah, you don't drop on that beach immediately because it might hurt. But when you have a very sandy beach, like we have in the north of Holland, you can drop there without any problem. Size matters, of course. It's the same material, exactly the same, but the properties are completely different. And this is what I want also to say. When you go to nanotechnology, molecular scale, etc., properties change, the behavior change, etc. So I get always the question, how do you know what you have? Of course, we have all these techniques, but now we have also the different microscopes. And here again, I want to emphasize that it's so important that we cross disciplines, that we cooperate, and especially also in these ERC programs, this is made possible because you get these programs where you can work on very fundamental challenges for several years, and you can work together, broaden your horizon scientifically to work with colleagues in different fields on very tough problems. And for this work, you know, we also cooperate with groups that do the scanning probe microscope, because you cannot use an ordinary microscope. It's micro. It's way too large. So the physics community have developed these new microscopes, which are like a needle, the end and the tip, yeah, with one atom. And you can then scan a surface and you can feel and see atoms and molecules. And you see IBM, who was very pioneering in this field, they could write nano USA with carbon monoxide on the surface. Excuse me, and realize that with at this level, you can write 250 million letters on the cross section of your one hair. So that gives you an impression of the size we are talking about. So our journey, as I mentioned, started with making responsive functions in the human eye. And so the first switches were based on this whole idea that with light, you could switch between two states, and maybe we thought we can do optical computing or information storage and use them for dynamic control of function. And so this is the light switch in your eye. It's a band molecule, and you can switch to a more linear molecule. You see here that you have two states, and we call them 0 and 1. And there are millions of these switches in your eye. And crucial, of course, is that they switch back. Otherwise, I would see you only once, and you would see me only once, and then it would be over. But this signal, this change in molecular structure upon irradiation with light, triggers a signal to the brain, and that makes it possible that we can store information and that we can do informational processing. So you might ask, why not using these molecules then and build a computer or build an information storage system? But that is not possible because they are way too sensitive. So what we did is we built artificial molecules, and this is one of our first designs. We built these helical type structures, M and P, minus and plus. They are completely artificial. They are very robust, and we can switch with light of two different wavelengths, 365 nanometer and 435 nanometer between the two states. So this is a really optical molecular switch made by molecular design, and it's about 1 nanometer or even smaller in size. And we made all kinds of devices out of it over the years. We cooperated with the physics people. And to show you an example, we made a piece of plastic where we could write data. And to give you an impression, you know, what we could do with nanotechnology, you make a compact disc. Of course, compact disc is now old-fashioned technology, but in principle, at those days, this is now 30 years ago, we could write zeros and ones in a piece of plastic. Now, you can calculate then what you can store on one compact disk if you can write information at the molecular level. And that is this kind of megabytes. So it sees that with one compact disk, you can store 250 years of music. So your grandparents and your grandchildren, 6 generations, can continuously play music. But this is, of course, not reality. This is what you see sometimes in magazines with the promise of nanotechnology. Yeah, but you have to be a bit careful what is written, because we don't know how to do this yet. Yes, we can write zeros and ones at the molecular level. We can write information. We can switch between the two states. But then I have to admit that you have to separate these zeros and ones, the molecules, a long distance, because if they come too close together at the nanoscale, we don't know how to address individual zeros and ones. So this is an unsolved problem even after 30 years, but you see some of the potential, if we ever solve this problem, what it means for information storage. But more recently, we have been working on photopharmacology, because we thought if we can switch with light, wouldn't it be cool if we could make precision medicine? And the idea is that you have a drug, a pharmaceutical that is inactive. You build in a light switch by synthesis in the laboratory, and then you activate it with a flash of light. So imagine you have a small infection in your body or a small tumor. You take a drug. The drug normally is active and affects all parts of your body. And for instance, with an antibiotic, you get all the problems with the bacteria in your guts. But what we want is that it's not active unless we irradiate precisely at the spot there where it's needed, where the infection is, for instance, or where the therapy is needed. High precision in therapeutic action by switching a medicine on and off. And so we worked on 2 important problems, at least that is what the World Health Organization tells us. One is bacterial resistance. We all face the COVID crisis, but the World Health Organization tells us that bacterial resistance is one of humanity's ticking time bombs due to the overuse of antibiotics. And we all know that this is a serious problem. Every year, 1.6 million people die of tuberculosis. And we have really serious problems with bacteria building up resistance against common antibiotics. Cancer treatment, we all know the nasty side effects of chemotherapy. High precision therapy could be very useful. And what I'm going to tell in the next few slides, I want to emphasize this is very early days. This is very fundamental science, proof of principle, and it's very far distance to the clinic and to applications. But we have to start somewhere. And what you see here is an antibiotic where we build in a light switch, and we have an off state and an on state. So in one form, the stretched molecule, the more linear molecule, it's off, and more bent molecule, it's on. And we can change antibiotic activity, switching it on, switching it off with light. And you see here below, everybody who has ever experienced growing cells, you see here a Petri dish with cells, bacterial cells growing. So in our lab, we grow this bacteria, we cover it with a mask, and then it depends on how if we irradiate, yes or no, yes, if the antibiotic is on or off. So where we don't irradiate, the bacteria grow normal, and when we irradiate, we switch the antibiotic on, and the bacteria don't grow. And the beauty is that we can precisely control it when it goes back. So the idea is you switch it on, and then after a few hours, it switches back and the antibiotic activity is gone, the bacteria grow normal, and you don't build resistance. So once again, it has to do its job precisely there where it's needed. And then after 12 hours, 24 hours, whatever, it is off and it does not give any side effects. We tried this also with precision chemotherapy. And you see here a typical bortezomib, which is used in the clinic. We build in a light switch, these so-called azobenzene light switches, which are very popular and used by many groups, and particularly also Professor Stefan Hecht, who is here in the panel, is a very prominent scientist in the world in this field. You see here what we do. We build in these azobenzenes, and we can switch on to some extent, indeed, the therapeutic action. And of course, once again, this is working in cells. This is not being used in the clinic yet. That is usually a long trajectory. But then I come to a serious problem here. And this is where several groups work in this field. And that is how to avoid blue or the ultraviolet light. Because you know, when you go to the beach in the summer and there is sunshine, you have to use sun cream to protect yourself, because you know ultraviolet light can be dangerous. So there is, of course, a big challenge here, how to use red light to make this working, because red light, infrared light, is innocent. It has high penetration depth in your body. You can use it also under the skin, and that opens up many new opportunities. And you see here in the bottom many names of people that are working in this field. And you see also, this is typically what synthetic gammas do. We modify the molecules and we can go through the whole visible spectrum and switch on with blue light, with red light, with purple light. And now in the latest results that have been published in recent years, we can, including our group, but also many others, we switch now on these kind of drugs with red or near infrared light. And that opens up a lot of opportunities for the future. So there's always the connection between the arts and sciences, creativity and imagination. We should not forget that when we enjoy the beauty of science. And if you ask me what is a beautiful molecule, I don't have immediately an answer, because it also is a first personal taste. Like you think of a beautiful flower or a beautiful painting or a piece of music. But there was a photographer who was at several labs, an international photographer, making pictures of scientists and science endeavors. And what you see here in this photo is the fingers of the PhD student in my lab who made the first red switchable antibiotic. And you see red light goes straight through your fingers. And this was in an exhibition. And how nice can it be that you bring arts and science of these young people together? So let me talk a little bit then about molecular motors. And we all know what a motor is in your car. We also know that your body is full of motors, because otherwise I could not speak and we could not move. And what does a motor do? A motor pushes a system out of equilibrium. Realize that your body is out of equilibrium. If you read in a magazine, I see this, sometimes I see this on television, that people say in these programs, be in equilibrium. No, please be in harmony or in balance, but don't be in equilibrium, because if your body is in equilibrium, you are dead. You are constantly pushed out of equilibrium. That is what a living system is all about. So what is the most beautiful motor that I know? That is this rotary motor. This is the ATPase rotary motor. There are millions and millions of these motors in your body, and they make the fuel, the ATP, the fuel in your body. And believe it or not, they make half your body weight every 24 hours. When I heard this figure from my biology friends, I couldn't believe it, that your body makes half the body weight every day. Now, you don't eat half your body weight, even if you have a very nice meal, but this is all recycled. And that brings us to the components are recycled of this fuel. And this brings me to a very important point. We are all discussing about recycling our materials, our plastics, all these things, you know, the components of your smartphone, your electric car, the batteries in the future. Ladies and gentlemen, we are simply not smart enough. We have to do inventions, discoveries, because your body recycles half your body weight every day with these tiny machines. So what are the fundamental questions that we had to ask to build a rotary motor? And this is the fundamental questions: how to control rotary motion in the nano world, and how to control left and right. First of all, you have to power it, like in your car, you have to put in energy. That is what we do by the light. And second, you have to control left or right, because if your car has equal probability going backward or forward, you stand still. Now, how do we control left and right? We look at chirality, the left-handed helix or the right-handed helix, you know, your right hand or left hand. The most beautiful example is the right-handed helix of DNA, the Mona Lisa of modern science. And so this is what we did. We built molecules in one form, only right-handed molecules or left-handed molecules. And then we could build this tiny motor that is rotating, as you can see. It's powered by light and is rotating in a unidirectional sense. clockwise or counterclockwise. If we take the right-handed form, it rotates clockwise. If we take the left-handed form, it rotates counterclockwise. This is this is the smallest rotary motor in the world that I know. It's 1 nanometer in size, 1 billion of a rotation. And if you irradiate with light, because you have to fuel it, it rotates spontaneously. So this is what happens. It goes in 4 steps and it makes a 360-degree rotary cycle. Now you might ask, when you discovered this motor, how fast was it? Can you build a car with it? Now the initial motor was rotating once an hour, and so it was very slow. But meanwhile, we have built dozens of different motors in the past 20 years. And the fastest one we have now is rotating 10 million times per second, and everything in between, for minutes, hours, but also milliseconds, and everything. We can control precisely the speed of these motors. Now, the big challenge is now, of course, to use these tiny machines and these rotary motors to work more complex motions. And I will show you a few examples what we do with it to give you an idea where fundamental science brings us to. First of all, my students, we were discussing about connective motion. And what you see here 2 types of motions connected. One is a rotor and the other is a motor. And it's all driven by light. And this is a stepping stone to more complex machinery. And here my students were actually looking at the moon, to synchronize motion, because you all know that the moon has a particular way of its motion synchronized with the earth, because you always see the same face from the moon. So it's not that my students are so romantic in Groningen, excuse me, maybe they are, that they look at the moon all the time, but in this particular case, we were fascinated by the synchronized motion, and this is what we built. So this is a stepping stone to more complex machineries. But what fascinated us even more is how to amplify motion. And now I have to go a little bit more deeper into the design. You all have a display, your smartphone, your screen of your laptop, etc. We all know that these are liquid crystal materials. These are rod-like molecules, and they are organized like beams in a river. And when we put a tiny amount of our motor in there, 1%, they organize in a helix organization. And it's well known that a colored pixel in your display, in your smartphone, you make it by contracting and expanding this helix. So if the helix becomes shorter, you get a blue pixel, and by expanding it, you get a red pixel. This is the so-called Bragg reflection of the light that we know from physics. So to put in this motor in there and rotating it, it changes the organization, and you see all the colors appearing. So we can make color pixels using these molecular motors. But what brought us even more excited is this. My students put a thin film of these soft materials, because liquid crystal materials are soft materials, on a glass plate. They put a tiny amount of these motors in there, and they put a glass rod on top of it. And I will never forget, this was a really eureka moment during my career. It was 5:15. My students said, Ben, come to the lab and have a look. And then they switched on the light like I do now, and hopefully it works. You see, when they switched on the light, the whole surface, all these waves on the surface, they started to move. The glass rod started to spin in a clockwise fashion. You see all the colors changing. So we have now a responsive surface, and it's all autonomous. It's just the energy of the light. So this was a real eureka moment in my career that I saw with the naked eye, the effect of our motors amplifying to a responsive surface. And so recently, and I will show you some very recent result, we have made artificial muscles. We make these motors now in these liquid crystal polymer materials. They are more robust. So you see on the top here, we can make an artificial muscle that can bend. And in the bottom here, you see a piece of plastic with these motors inside. And ladies and gentlemen, we have now a piece of plastic that walks over the table when you irradiate it with the lamp. So it walks towards the light. I don't know how many pieces of plastic you have that walk over your table, but this is what molecular motors can do. And this is what you can do when you have this motor function and you have collective action. They amplify all the way to macroscopic levels. So this gives us now the future opportunities, maybe for soft robotics, because this is going to be a really important field in the future, of course. We all know that, but we have to make the fundamental discoveries, and that will, of course, be very important, not only for materials, but also for the biomedical field, soft robotics. So coming from the Netherlands, we also like windmills, and you see here the traditional windmill with the tulip fields. Please come next month to the Netherlands, because the tulip fields are soon starting to blossom. You can see the traditional windmills. We have also in Europe and also in Holland, of course, the modern windmills. And we thought, in the good Dutch tradition, we should build a windmill. So you see here the design. We have a rotor, we have an axle, we have a stator, and we have two legs. And we built it initially on gold, but we can put it on any surface that we like. So we built a nano windmill park. You see the traditional windmills, 20 meters in size. We have one who is 2 meters in size, 2 nanometers in size. It's 1 billion times smaller. 1 billion times smaller. So all these propellers, these nanomotors, rotate, yeah, in a unidirectional sense. Now you might ask, this is very fundamental science. This is playground for academics. Why is this useful? But remember, when you can make a responsive surface, you put them on glass, as we did, you can make self-cleaning windows. You can clean your solar panels. Usually we don't have a big problem in the north of Holland because there's a lot of rain here. But when you go to more sunny areas, you have a lot of dust and you have to clean your solar panels. Imagine they clean themselves. Your cars in the future, you know, you have coatings because they are mobile, they will clean themselves. And self-repairing. If you have a scratch in your finger, yeah, and you keep it clean, it repairs itself. But when they are mobile, yeah, they might repair itself also when you have a scratch in your car. So this is the future of this kind of responsive materials, taking advantage of the fact that we can make our dynamics and motion. So we built also a molecular car. This is our molecular car. We were very much inspired by this solar power driven cars that the engineers built. We built a 4-wheel drive. It's 2 nanometers in size. Again, 1 billion times smaller. It's powered by solar energy. And this is the real molecule. And you see it moving here because, again, we use the scanning probe microscope, these new microscopes. This is work we did together with the university in Zurich. And we could actually see it moving over the surface. And this was very tricky. It took us 8 years to build it because you have the wheels correctly spinning. Yeah, we can discuss this later because it's very important. But what was the real challenge here is not to build a car, of course, but we want to see if we could put rotation into translational movement, moving forward or backward, just like with a normal car. And this is actually what happens at the nano scale, ladies and gentlemen. It's not like the world is completely different. It's not like the motor on in the car in the street. This is how the car moves over a surface. And this is actually how the motors walk on the muscles when you lift your arm. There are millions of these motors that make your arm lift due to this muscle function. There was, just to give you an impression that this is really happening, I'll show you this small movie. I borrowed this from Harvard. And you see this is happening now at this moment in your body. And then you will see that my presentation of how these motors move and how this car moves is not so weird. You know, the highway, yeah, the motorway is built if something has to move and is disassembled when something has passed by. And now you will see how things are transported in your cell. This goes at an enormous pace. Yeah, millions of these machines make things transporting in your body, like the walking machines. This is the nano world. How does the car look? This is a modern electric car. Here you see our nano car is this white powder. 1 billion times 1 billion identical nano cars. This is what we make. Our car manufacturing plant is not so bad after all. And there was also a nano car race in Toulouse in 2017. The first ever Formula 1 race for nano cars. So probably there will be another one not too long from now. So entering an adventure with nature, it's a playground for science and education. And so you have to ask yourself, which scientific question or problem do I want to address? Originality and adventure. Don't be afraid. Value your PhD students, the young talents that you can work with every day. Teaching and research, this combination to create enthusiasm and curiosity. And what I experienced, you have to be a bit convincing critical, but also it needs a lot of perseverance. International focus. Which signature do you want to give in Europe and in the world? And enter a league instead of avoiding competition. So where do you want to play? What is your playground? And people always say scientists work hard, of course, but don't work only hard. In particular, I can advise you work smart. That's more important. So people ask me then, and I'm coming to the end of my lecture, can you build a nano submarine? And I discussed this with my students, a submarine that could through your blood veins. It's a bit of science fiction, eh? So we discussed about something else than light. And indeed, we asked ourselves the question, what would be the fuel? And so we decided to make a nanotube with 2 enzymes that could convert sugar, produce oxygen, and propel the system. And this is actually our design. You see here in our fantastic voyage, we were able to build this nanotube. You see this tiny spider here, and it moves completely autonomous. The bubbles here is oxygen coming off, and you see it moves completely autonomous, as long as there is sugar as a fuel. This is the farthest we got. The movement is not very very controlled yet, but it moves completely autonomous with sugar water as the fuel. So will we have nanorobots? And is it science or science fiction? I predict that in 50 years from now, the surgeon will inject a nanorobot in your body to go to look for a defect or to deliver a drug or do a repair. We know now that we can make movement, autonomous movement. We can control functions already, but I'm not very good in prediction. So the best way to predict the future is to invent it. And that is what we do together as scientists, together as ESC grantees, and particularly made it possible through all the ESC support that we get for our science. So to summarize, we exploit molecular motion, we make switches, we make autonomous motion, you see a translation, you see rotatory motion, all kinds of motion. Everything I show here is autonomous motion that we have developed over the past years. I don't want to go into detail because my time is over. I want to give credit to my students. We share a passion with the young people. They are my heroes. They do all the discoveries, and inventing our future is made possible through these young talents, sponsored by the European Research Council programs, and I'm extremely grateful. Now, when I was a young boy, did I know that I would be a scientist? And so what final lessons I want to give to you, what I learned: discover your talent, follow your dreams, be confident, discover your energy, and discover your limits. Going in this adventure in the unknown, what is your passion? And particularly, follow your dreams. Don't give up too easy. So, did I know that I would get a Nobel Prize when I was a young boy? I showed you where I grew up. And no, I was working on my science. And I actually was never much aware of this whole Nobel Prize thing until 2011, when I got a phone call from a colleague from the United States. He called me at 9 o'clock or 9:15 on a Tuesday evening. And he said, "Ben, you were on American television." I said, "Come on." He said, yes, you were on primetime American television. Look, this was a week before the announcements of the Nobel Prize. And he said, in The Simpsons, look, The Simpsons predicted chemistry, Nobel Prizes, Richard Tarr, Bill Murner, Ben Feringa, and Sonika Shira. Bill Murner got the Nobel Prize in 2014. I had to wait another 2 years. The next morning, the students said, "Ben, you will get a Nobel Prize." The Simpsons predicted it because they had seen this on the internet. I said, "Look, guys, maybe I don't need the Nobel Prize." Can you imagine? I was on American primetime television, predicted the Nobel Prize by The Simpsons. This is the highest honor you can get probably in science. But then I got a magic call from Stockholm, and I got this award, and I'm extremely indebted. And I'm extremely indebted also to all the grant agencies, including the ESC, who made this all possible, because it's very fundamental science. We don't know yet where it will lead to, but I can guarantee you some of these principles will change our world in the future. And maybe one of the best recognitions I got, that when I was in Berlin not so long ago, I saw this on the wall. Our motor, you know, with 3 legs that we put on the surface, and apparently an artist used it in his graffiti. How nice can it be for a scientist that you find yourself back on the wall in a graffiti painting. And I want to finish in the joy of discovery. I want to remember you of Leonardo da Vinci, my hero. He said 500 years ago, when nature finishes producing its own species, man begins with the help of nature to create an infinity of species. And for all the young stars in the audience, imagine the unimaginable. And with that, I would like to thank the organizers and thank you for your attention. Thank you so much.
Well, thank you, Ben. Thank you for this wonderful presentation. Truly inspiring and exciting what's going on in this field. I already love the playground of the nano world. And coming from the Netherlands, it's good to know that we get new windmills or new mills and new nano robots in 2073. So
maybe, and maybe you don't have to wash your windows or your car anymore in the future. But I don't know if it will be with our motors. But once you know the fundamental principles, you can dream about a lot of applications. Thank you.
So I will now invite one of your good colleagues, Professor Stefan Hecht, who is currently the Einstein Professor and head of the Laboratory of Organic Chemistry and Functional Materials, as well as the founding director of the Center of the Science of Materials in Berlin and at the Humboldt University. So Professor Hecht has a long list of prestigious appointments. He's a group leader in organic polymer and materials chemistry at the Max Planck in Mülheim an der Ruhr. And he is full professor at Humboldt, scientific director of the Leibniz Institute for Interactive Materials in Aachen. And he has a long list of prestigious awards, among which the Einstein Professorship and a fellowship of the Royal Society of Chemistry. A long, long list. Dear Professor Hecht, thanks so much for being here, and over to you.
Thank you very much for giving me the opportunity and also for listening to Ben's talk. I listen to Ben's lectures quite regularly. We work in the same field. You could see that from his presentation, and I still enjoy them, which is probably the best compliment I can give to Ben. And I think what I really truly admire, Ben, is your passion. I think you nail it down quite well. The passion for science. I think the curiosity is super important. And I'm also a big fan of quotes. I recently ran into this Linus Pauling quote, and Linus Pauling was one of these people who actually got 2 Nobel Prizes, but one was for chemistry and one was for peace, which is interesting. And the quote is, "Satisfaction of one's curiosity is one of the greatest sources of happiness in life." And I actually really think that doing science is a great formula for being happy. At least I feel very privileged, and I know that Ben does as well to do science. So I gotta ask some intelligent question, and it should not be, I think, relate too much to science, but more for the program. And I think this is you nicely illustrated how important it is to be curious and to choose the problem. I think you quoted the old Feringa with "choose an important problem." That was a very good advice, and I think it is a good advice. The older I get, I'm still young, is the importance of asking the right question is actually something that we should cherish more. And so, as we are discussing, my question to you, Ben, is, where do you see the problems? I mean, the ERC is great, and that it should come from the curiosity of the researchers of the young and next generation to drive our society and to do research that has impact. But where do you see the dangers or the challenges, not in a scientific field, but maybe in our realm? In our realm that we also face, teaching, recruiting, inspiring, getting young people to do science. Where do you see the challenges?
Yeah, I think thank you very much, Stefan, and I'm so glad that you are here in this panel, and we know each other for a long time, and it's really amazing how you bring also the field forward. This question is really important, where are the big challenges, you know, and what are the dangers, you know, that approach it, because we can have these nice fundamental science programs like the ESC programs and so, but most important, of course, is that we stimulate our young people with these curious minds. And nowadays, there is, of course, a lot of pressure to go also for short-term success. So they say, oh yeah, we have the problem, you know, with the COVID, we have the problem with the sustainability, we have the problem with the environment, and etc., etc. Of course, this is important, but we should be very careful, because the problems, the solutions might come from a completely different angle, and we have to. Everybody, when you do teaching, when you are how to call trained, you know, you learn certain perspectives, certain views. We all build upon our teachers, about the knowledge, you know, that we get from the literature. But it's, I think, extremely important that we train our students to think also a little bit out of the box and not taking everything for granted. And I remember when I give first year lecture to the first year undergraduate students, I often start with saying, look, don't believe everything is in the book. And then they get very nervous, because in high school, they are often taught, you know, okay, what is in the book is true. But we all know that it is the best knowledge, maybe the models, the insights, the mechanisms. When I talk about chemistry or physics or mathematics, that is the knowledge we have at this moment. But that's based on the models, the data, the insights, the experiments, the theory that we have at this moment. And that is constantly changing, you know, so the insights might become different in 5 years from now. So this critical attitude and also this creativity, we should train them, and it's extremely important. And what is also struck me is, I go to schools quite often now, elementary schools and high schools. You know, we built this foundation to visit schools and to encourage the teachers, but in particularly the kids in school, and to stimulate this creative mind, this curiosity from an early age on. Because when you go to elementary school, the students still, the kids have a very curious mind often, you know, 5, 6, 7 years old. They are unspoiled, let me say it bluntly. And to stimulate that and to bring that forward, you know, all the way to the students we also train, and to make this also clear to the people in society, and so that you need sufficient space for curiosity, for asking questions, also to make mistakes. All these kind of things is really important. And so that is where we have a big challenge, you know, to bring that forward. Yeah. Because with all respect for politicians, but politicians often think in one cabinet period, you know, 4 or 5 years. But of course, many of the issues that will make really breakthroughs take much longer. Think of COVID, the new vaccines. I mean, the RNA technology was developed in the early 80s, you know, by Kathleen Carrigo and so. And we cannot develop a vaccine in 1 year. It took 30 years of basic research. Yeah.
Yeah, I think this what you bring up, the short-term thinking is a very good point. I see this as a big problem, not just for science and politics and decision making in general. And it's interesting. I looked this up. You might remember this. There was I think some scientists in more than 10, 12 or 13 years ago, I looked up in 2010, Slow Science Manifesto. They were basically saying something that is very important. We need time to think. Yeah. And we need time to think critically, and only then we can really give valuable advice to society. And something else that you said, I think was very good, is the process of advancing, of finding or approaching the truth is a process. It never ends, right? And I mean, this is what the old Greek philosophers knew already. And there has to be it's very difficult to get that into a mind of a politician who has to be reelected and who wants to quantify the output of the funding that he gives you, right? Yeah. And I see this as a big challenge for science. If I may, so my question is, you have to deal a lot with politicians. Yeah, my immediate response is, you know, I fully agree with you. This whole mindset, you know, and that is also why for us it's important that we go out to the public, to the politicians.
I think each of us has a duty to make this possible. And I would not be unhappy if we as scientists get an ERC grant that we would, I know there is also a journalist in the audience, that we in the panel, that we would get more or less the duty to write, if we do a discovery or whatever, also to write a more popular piece that makes it clear why this scientific discovery or the advantage of knowledge is so important, you know. And you might not immediately solve a societal problem, but in 30 years from now, it might make a real difference. And you are absolutely right that at the universities, we need a bit of time also for thinking. So the advantage of an ERC grant is, of course, that you have some solid funding for a few years, and it gives you time also to think, to space to be creative. And this is something that we have. I'm sometimes a bit jealous of the old generations of professors, you know, that have much more time to think. They didn't have to write so many grant applications and reports and ticking boxes. And so nowadays we have so many administrative forms. But you know what I mean, having time to think. And the COVID crisis, although many people complain, me too, yeah, because we were limited in many things. It had also a benefit that we were more at home, we had more time, we could not travel, and at least, I don't know about you, but I had more time to think. I had to read, I could read a paper decently, and I could really think a little bit more about challenging problems. So it has also a benefit, you know, to create ideas. And this is crucial indeed. Not only think about...
We have to go on.
Yeah.
We have to go on, but this is a discussion to my heart, and I'm very jealous too of these people that have more time.
Yeah.
Thank you so much. So thank you, Professor Hecht. I would like to now invite Joep Engels, who is a well-known science journalist in the Netherlands and also physicist by training. And you got to know Ben Feringa, I think, in the 90s when you were a science editor for the newsletter of the University of Groningen. And since 1996, you've worked for Trouw, which is one of the Netherlands' most well-known daily newspapers, and which was rewarded in 2012 with the European Newspaper Award. So, Joep, great that you're here, and your turn.
Thank you, Ben, for this beautiful presentation. Accidentally, I was 2 weeks ago, I saw you also when you gave almost the same presentation, but then the audience were children for 10, 11 years old from a primary school at the north of the Netherlands somewhere. And it's really fascinating that you can give this talk to a scientific audience like this and to these primary school children.
Well, I had to change for the school kids. I had to change a little bit, you know that, but, yeah. But they had also questions.
Yeah. But what fascinated me is you and your group made great achievements with to make molecules move again, and you talked about all these fascinating applications like in the medicine and elsewhere. But I wondered how much does it contribute to our fundamental knowledge? You mentioned Richard Feynman, and he said also once, if I can't create it, I don't understand it. And you created moving molecules. So how does it fit in with understanding it?
Yeah, that's a very good point. Of course, I don't know exactly if Richard Feynman should be followed in all aspects, because I had this discussion also, I think, sometimes with Robert Dijkgraaf or these people from theoretical physics or astrophysics. If Richard Feynman says, if I cannot create it, I don't understand it, then it's very difficult to understand what a black hole is, or what an the black how do you call it, an implosion is, you know, the stars and all these things, because you will never be able to create it as far as I can see. But so understanding is a broader context. But of course, yes, we can create things, we can build things from scratch. And the whole thing, what I try to do is to build these tiny machines and moving objects. And it gives us, of course, a lot of insight in how you can get mechanical functions at the molecular scale. How does this operate? How you can get light energy making controlled motion. Yeah. And so the fundamental understanding of how this works, and I did not discuss this in detail, gives us a lot of insight also in how Mother Nature operates. How do these molecules in cells operate? How does it operate in your eye? Because in fact, I learned from my American colleagues, which are in the biophysics field, that the machine in your eye is almost working the same as our motors. Yeah. So nature, yeah, I think we can be a bit modest here because nature has invented this already, you know. But this is the main thing, you know, that you get these kind of fundamental insights. How can you make a rotation? How can you make a translational movement? How can you couple things together? How can you amplify, you know? Yeah. I don't know if it answers all the question, but at least this is where we.
Sorry, I missed
You
the
muted
last.
yourself,
Sorry.
Ben.
So this is what we are aiming for, to build things, to get function on the molecular level at the supramolecular microscope, but also how to understand how it operates. And we use that all the time. We use also theoretical methods, calculations to try to precisely understand the details and then to design better systems, new systems and whatever.
But is this nature an example, or do you learn
No,
how nature works by trying to?
now nature is an example because, you know, we learn, as I mentioned, the flying pigeon and the Boeing. Yeah, I mean, they are not the same principles, etc. So we can look to Mother Nature, but we don't have exactly to copy nature. You should realize nature also built. So I want to understand fundamental principles, yes, yeah, and to apply it. And taking inspiration of nature is great, but we are not limited by the building blocks of nature. If you look at the limited set of amino acids and the nucleosides, you know, that are used for DNA and the peptides and the sugars, it's amazing that Mother Nature builds your body from a very limited set of molecules. We have unlimited possibilities of making molecules. We have scratched only the surface, you know, of what is possible. And so building artificial systems, yeah, being it a piece of plastic, yeah, or being it a drug, yeah, or being it the components of your, I mean, there is so many opportunities there that we have not even touched upon and that we can explore. And of course, they will not be the same as Mother Nature, yeah. But this is what is the beauty of science. I mean, imagine, I can ask you a question. Nature in evolution never invented the wheel as far as I know. Yeah, mankind invented the wheel, but it's not based on natural molecules. At least not the wheel of my car. Okay, you can use natural rubber, but usually we use artificial rubber. But this is the opportunities and possibilities, yes. But still, we get very fundamental insights, indeed.
And you called your speech the joy of discovery.
Yes.
And we all know this feeling that you have been working very hard and walking the wrong direction, and at last you get the answer, and it's really very exciting.
Yeah.
But I was wondering, there's also this period when you can almost grab the answer. You feel you're very close to it. That stage is also very exciting.
Yeah.
How much is it blinding your view? So do you know what I mean? That you
almost there.
Yeah, almost there, and then not anymore aware of other possibilities.
Yeah, I think this is a very important point. First of all, of course, when you are close to the finish, that you have established something or proven something, it's always the pressure, you know, how to finalize and how to get it really done, etc., etc. But also that you then focus completely on that, and that you might forget other options and opportunities. That is to keep a certain balance, you know, because if you continuously jump on new things, yeah, you are so scattered that you will never finish something. Yeah, that's also not good. So we have to push ourselves also to complete something decently, and sometimes it's just hard work. Yeah, getting the examples done, getting all the controls done, etc. That can sometimes be a bit dull, also for a student, a PhD student, and so. But sometimes it's really necessary when we develop a new chemical method. Yeah, in synthesis, for instance, you don't want to do one chemical reaction, but you want to have maybe 30 examples that you see, oh, this has a certain generality that my colleague, Professor Hecht, can also use it. And not only for my molecule, but also for his molecule. Then they are very happy. So this is what science is also about. And that sometimes is just, yeah, making small strides. Yeah, it cannot be always party time in science.
Okay. So thank you, Mr. Engels. Thank you so much. So I'm now going to invite our third panelist, our very own Silke Bühler-Paschen. Silke is a founding member of our association and a 2 times recipient of an ERC Advanced grant. So Professor Bühler-Paschen is a condensed matter physicist at Vienna University of Technology, and she held appointments in Switzerland, Germany, Japan, US, including at the AERG in Zurich, Max Planck Institute for Chemical Physics of Solids in Dresden, and Rice University. She's a fellow of the American Physical Society. And importantly, she and her team design and study novel quantum materials, a field with close link, I would say, to solid state chemistry. So Silke, you have the mic.
Okay, thank you very much, Karin. And thank you so much, Ben, for this really totally fascinating talk. In particular, I really loved your entrance with showing the periodic table over and over, because I do that very frequently. I work in condensed matter, but we use, of course, the same elements. We don't have anything else. We put them together in a solid, and it's very interesting to see what element has actually which role. And I do very similar entrance to my talk. So I had one specific question before I have some more general ones. So what are the elements making your molecular cars? Is there any magic element, or is that essentially carbohydrates?
Yeah, it's just carbon, hydrogen, nitrogen, oxygen, if needed. You know, that depends upon the substituents we put there. But basically, the skeleton of all these molecules is carbon. Yes.
Yeah.
So typical organic molecules. But we have also made
not special roles by special atoms, or is there something?
No, that you can tune the properties, of course. That's what we constantly do. Tune the properties, like the electronic properties, the optical properties, all these things, by choosing the different groups that we put in there, you know. So sometimes we need a nitro group, sometimes we need an oxygen, sometimes we need some other groups, you know, to change, so for instance, the energy levels or the sterics in the compounds. You saw this example of this red light switches. Yeah. So there, and Professor Hecht also works in this, as I mentioned, we introduce all kinds of substituents to tune the absorption spectra of the light, and then you can shift all the way through the spectrum. So this is typically what synthetic chemists do, changing the material. But this is also what you do in solid state materials. You change the atoms, you change with dopants, you put in some tiny amounts of lanthanide, you get completely different properties. So this is the beauty of engineering with a periodic table and with molecules.
Absolutely. Okay, thank you so much. So then I saw from your CV that you have really very successful career in applied research, like you have 30 patents, which is a crazy amount, and then you have 2 ERC grants. So are these totally separate directions of your research, or do you sometimes combine both? Because I find it pretty hard to combine my research with applied aspects. So what is it for you?
Yeah, that is a very important question. I'm a chemist, you know, and we also have quite a few cooperation with industry. So over the years, in the past 30 years, the basis of my research has been fundamental research, you know. And so I want to work on these fundamental aspects. So being it catalysis, chemical synthesis, these molecular machines and materials. But we also had some programs always together with industry. So on more say applications towards, okay, what is a fundamental problem, you know, in industry? So for instance, working on oxidation catalysis, activating molecular oxygen. This is a real important problem, for instance, for making detergents, or for bleaching paper, for instance, paper industry, all these kind of things. And so we work together with Unilever. For instance, we have a couple of patents there, out of this series, making bleaching catalyst for dishwashing and for your wash powder.
But it must be constantly on your mind to even think of these aspects.
Oh, yeah, when we work on these problems, we can think about what are potential applications. And now to give you another example, we established together with colleagues in Utrecht University, Bert Werkhuizen, you might know him, and other people at Eindhoven University, the engineering school there. We established a national center 5 years ago for sustainable chemistry. And so we brought together homogeneous catalysis, heterogeneous catalysis, material science, and engineering to build on challenges from industry, also industry Shell, AkzoNobel, BASF, they are all involved. And we are working there on sustainable process and materials. And just to give you an example, I think we have now 6 patents or so together with them. That is on making coatings, yeah, paints and coatings from the wood remains. So instead of burning wood, yeah, we take this remains of wood and we make acrylate building blocks. So they are mimics of, now you know acrylates are everywhere. Eh? They have produced millions of tons of acrylates for the painting your house, making the coatings of your car. So talking about materials, we have made now acrylate replacement that Akzo has tested, and they seem to be as good. The first test showed that they are as good as the coating on your car. Now, so we are extremely happy. So bio-based material into a real life product. So this is the kind of projects. I don't do this on my own. We cooperate, we team up with people in industry, etc. But for students, it's also interesting to work on fundamental new approaches, looking at it from different angles, you know. And in material science, there are tremendous opportunities, of course, also. Eh?
Yeah, definitely. But you could easily get sidetracked to that either or, right? But you seem to juggle the.
No, yeah, that is also, you are absolutely right. This is the important point, because you should also realize that you are at a university. And I think the basis of the university is fundamental science, advancing knowledge. And we should build on that. And we should not forget that. We are not a company. We are not an industry, you know. We are a university. But there are plenty of opportunities to bring it further.
Okay, thank you so much. So I have one more science politics question. So you are just in the start of your second period as an ERC Scientific Council member, right? So
yes.
Of course, we are very, very interested in your work there, because we try to come from our side and promote research like the one funded by the ERC. So what are the current challenges? Can you say something about challenges the Scientific Council is facing? Or also the other side, what's the most exciting or interesting ideas that you are discussing now? Are you allowed to tell us, or?
No, I cannot talk all the details, but I mean,
sure.
Last year, very challenging was, of course, to establish the New Horizon Europe program to get sufficient money for fundamental research, because we have also the European Innovation Council, and there are many other programs which are more on applications. And we had to fight a lot, honestly, to convince the European politics that we maintain this good basis in fundamental blue sky research. And luckily, you know, I think the budgets did not go down. We had expected maybe a little bit more to increase them, but at least there is a very good budget in the coming years, and we are extremely happy with that, because this is the basis, this is the fundament. Now, the other point, you know, to get a little bit more ERC grants in Eastern Europe, you know, I would say in those countries in the Middle and Eastern Europe, there is a lot of talents, but there is not the kind of ERC grants that they get in Germany and France, maybe in Holland. And so we would like to encourage that a bit more. And of course, a serious problem is also England, the UK, and Switzerland, because Switzerland was in the European Council, and I think that is an issue now. And the UK with the Brexit is a serious issue. And I mentioned also to the European Commission, so we are dealing with that. And I mentioned to the European Commissioner, you know, we should build this European community together, because it's so important for our friendly competition, the science community. We try to play, you know, we try to play in the European League, the European Championships. Now imagine you play the European Championships with Real Madrid, Barcelona, AC Milan, and Bayern München, and maybe from Holland, Ajax. But we have Liverpool, Manchester United, or Chelsea cannot play. This is nonsense. It cannot be. We need each other. We need to compete with each other. We need to cooperate. I think all these things are important. And so this is what we are fighting for. And I think ERC grantees are really important to bring this message also forward. I mean, it's not about borders, as I said in the beginning, you know. Let's take this message of Pasteur clear. We have to cross borders. We have to unite. We have to join forces for the future of mankind. And especially we owe it to our young people.
Thank you so much. So, is there time for one very short last question?
Sure.
I'm sorry.
Okay, so
No, we have to continue. Thank you so much, Silke,
Okay.
for all these questions.
Okay, thank you.
We now have to move on. So I give the word to Simon, Simon will check if there's a question from the audience. I think there's one, and there's also one from here from another panelist. So please take the floor, Simon.
Yeah, thank you very much, Ben, for this really exciting lecture. So for the sake of time, I will not ask my own questions, but I will focus on the questions of the audience. So one question is, what movements or problems involving movements are common in nature or most difficult to recapitulate at the molecular level?
Yeah, problems in movement. Yes. Now, this is a very important question, you know, when you think about this, you know, you saw this propulsion with sugar as a fuel, these nanotubes, you know, this kind of submarine. There, of course, one of the key problems is how to control directionality, how to get much better control of motion. With our line-driven motors, we could put them on the surface and then we have much better control. But with these other motors, there's still a long way to go to the kind of control that nature offers, you know, and I know many groups around the world are working on that. And then, of course, and also another issue is in your muscle, when I lift my arm here, you know, I will do it in front of the screen. There are millions of these motors. They walk, yeah, on this highway. You saw that when I showed this movie. Now, to control this kind of movement on the surface, yeah, that is really tough. We are struggling with it already several years. Why is that so tough? Because they have to be able to move. So, and they have to stay on the surface or on a trajectory, but don't fly away, because molecules are also very volatile. They can move away, thermal movement, etc. So you have precisely to balance the interactions. So this is the very difficult interplay between adhesion and movement. And this is a combination of surface science, supramolecular chemistry, all these kind of things. Yeah. The other important challenge is, of course, to have concerted action. And as Silke was asking these questions about solid materials, we work on MOFs and COFs. And MOFs, for instance, these metal organic porous materials that you can build in these motors. We built motor MOFs. So we have these solid materials with these pores and we have motors inside. And now, of course, the challenge is how to get synchronized motion of all these motors, because then you can make really smart materials like new membranes for water purification and so. And so there are quite a few challenges ahead, yes.
Thank you. And then I will move on to the last question from Roland, from the panel with the panel member in the association. What are the perspectives of a nanosystem technology combining molecular sensors, molecular actuators, and molecular electronics?
Yeah, now I don't know exactly what the whole perspective is, but of course, when you can make sensors and you can change the sensor, you know, so that they adapt to the environment. So for instance, what you see now that people work on this artificial skin. Yeah. Now your skin is quite mobile, it can bend and whatever. And so to use this kind of nanotechnology to build this out of artificial skin with electronic components, but the electronic components also can adapt and sense. Yeah, this is a hot area and you will see a lot, I think, in the future in the biomedical applications. I think integrating smart electronics, technology, nanotechnology with, for instance, interface it with biological systems, like, for instance, smart skin, sensors and all these kind of things. Also, what people try to do is to introduce these kind of switches. And so Dick Trauner, for instance, he has a program where they introduce this into materials that can trigger neuron transmission, signal transmission. So to see if you could get, if you have some problems with your neural cords or the neurons, they have done some experiments in mice. This is absolutely fascinating, you know, that they can pick up signals again, you know, so transmit signals and so, because you have this kind of adaptive materials and adaptive functions. I think here, I would almost say the sky is the limit, you know, to integrate these different components. But that, of course, needs a delicate science, because you have soft materials, you have hard materials, you have biomaterials. They should be biocompatible. They should not be toxic. You should integrate optical maybe with electronic signal transduction. So this is a multidisciplinary aspect. And this is also beautiful because you bring several scientists together. I must say, I work now together with the people in the medical school on this photopharmacology, and people don't believe it. But I start studying again as a first-year student, cell biology and so. The reason is I have to know their language to be able to talk with them. The same holds for physics. When I talk with physics people, I have to know their language and they have to know my language. Then you can cooperate. So science is also about studying your whole life and being curious, but also to study the basic things, etc. And people said to me, you know, I was in schools and students said to me, come on, you got a gold medal in Stockholm. You don't never have to study anymore in your life. I said, look, I study like a first-year student. Otherwise I cannot talk even with my colleagues. I have to learn the language. This is also the beauty of science.
Wow, this is a beautiful end, I would say. We are coming to an end, and wow, thank you. It's the end of our 4th Science and Society event. Thank you again, Fernanda, Simon, Axel, and the Necker Institute for these events. Thank you to our wonderful panelists. But most of all, thank you, Ben, for sharing this joy of discovery with us today. It was really inspiring. We will now close the event, but please stay tuned for more series in our seminars, and please become members of our association if you haven't done so. And follow us on Twitter. And for more news, our account, I don't know if we can see it now here, but well, no, I don't see it now.
Okay. Thank you very much, Karin. It was a real joy.
And bye-bye, everybody.